Welcome back to another video. Today we're going to explore one of the most important steps in any machine learning project, understanding your data before training a model. We'll see how to identify missing values, detect duplicate records, investigate outliers instead of blindly removing them, and find inconsistent or suspicious data. Then we'll use exploratory data analysis to discover relationships and hidden patterns in our data. We'll also look at what correlation really tells us, how statistical significance helps us interpret relationships, and why correlation does not necessarily mean causation. And finally, we'll see how mistakes in the way we prepare and split our data can cause data leakage and give us misleading model performance. By the end of this video, you'll have a practical checklist that you can apply to almost any data set before training a machine learning model. So, are you ready? Let's go.
Before we start, here's today's challenge. Suppose we find a Pearson correlation of 0.82 between two variables, with a p-value below 0.001. What can we actually conclude from this? Does one variable cause the other? Does it mean this feature will definitely improve our machine learning model? Or does it simply tell us that we found a strong, statistically significant association? Please comment your answers after watching the whole video. For this video, I'm going to use the companion dataset from the book Applied Machine Learning for Data Science Practitioners. It contains 1,460 observations and 79 features describing vacation homes. Our target variable is the sale price. I'm not going to analyze all 79 columns. Instead, we'll use a few of them to understand the most important data quality problems you're likely to encounter in real projects. Before changing anything, we first need to understand what we're looking at. This sounds obvious, but it's one of the most common mistakes in data preparation. We see a missing value, so we immediately fill it. We see an outlier, so we delete it. We see duplicate-looking rows, so we remove them. But every one of those actions makes an assumption about the data. So throughout this video, I want you to remember one simple principle. Detection comes first, investigation comes second, the decision comes last. Here's another important point. The data type reported by Python does not necessarily tell us how a feature should be interpreted. An ID may be stored as an integer. A rating may also be stored as an integer. And house area may be stored as an integer. But these numbers don't mean the same thing. Calculating an average house area makes sense. Calculating the average record IDs usually doesn't. So don't ask only, what is the data type? Ask, what does this variable actually represent? This brings us to another common problem. Identifiers. Customer IDs, transaction numbers, email addresses, barcodes, and record IDs can look like useful features because they contain lots of unique values. But uniqueness does not mean predictive value. If a column simply identifies individual observations, a flexible model may memorize patterns that won't generalize to new data. That doesn't mean every ID must always be removed. Sometimes an identifier contains useful structure. But before using one as a feature, ask, will this information represent a repeatable pattern when the model sees new observations? Now let's look at missing values. A simple summary immediately shows something interesting. Around 47% of the fireplace quality column is missing. At first glance, that looks terrible. Almost half the column is empty. So should we drop it? Not yet. The first question should not be how much is missing. The first question should be why is it missing? Imagine a house that doesn't have a fireplace. What should its fireplace quality be? Good? Average? Poor? None of those make sense. The value is missing because the feature is simply not applicable. If we replace that missing value with the most common fireplace quality, we're actually creating false information. Missing values can have very different meanings. Sometimes a value should have been collected but wasn't. Sometimes a value doesn't apply to that observation. And sometimes the fact that a value is missing may itself contain useful information. That's why there's no universal rule saying that a feature with 20, 30, or even 50% missing data must automatically be removed. Once we understand why the values are missing, we can choose a more appropriate way to handle them. If only a small number of values are missing, and they appear to be missing randomly, removing those few observations may be reasonable. We could also impute them, depending on how much data we have and how important the feature is. For numerical features, Mean or median imputation are common options, but they are not interchangeable. If the distribution is fairly symmetric and doesn't contain strong outliers, the mean may work well. But if the data is skewed or contains extreme values, the median is often a better choice because it is much less affected by those extremes. If a value is missing because it simply doesn't apply, like fireplace quality for a house with no fireplace, we shouldn't replace it with an average or the most common value. A separate category such as not applicable would preserve the real meaning of the data. In some cases, the fact that a value is missing can itself be useful information. In that situation, we can create a missing indicator, a new binary feature that tells the model whether the original value is missing. And finally, if a large portion of a feature is missing, and we don't understand why, we shouldn't automatically drop it or fill it. That's a signal to investigate the data source, the collection process, or the business logic first. Now let's look at sale price. The mean is around 150,000, while the median is around 135,000. And the maximum price is more than 626,000. That difference between the mean and median already suggests that the distribution may have a long right tail. The histogram confirms it. Most properties are concentrated in the lower price range, while a smaller number of expensive properties stretch the distribution to the right. A box plot makes the unusual observations even easier to see. But here's the important part. A box plot does not tell us that these observations are wrong. It only tells us that they are unusual compared with the rest of the data. An outlier may be a typing error. It may use the wrong unit. It may belong to a different population. Or it may simply be a perfectly valid rare observation. And in some applications, such as fraud detection or anomaly detection, the unusual observations may be exactly what we're trying to find. So automatically deleting everything outside the box plot whiskers is a dangerous strategy. If the observation is valid, we shouldn't automatically remove it. For example, if a numerical feature has a strong right skewed or long-tailed distribution, we may consider applying a log transformation. A log transformation compresses large values more than small values, which can reduce skewness and the influence of extreme observations for some models. But again, these are not automatic rules. The right treatment depends on why the value is unusual and which model we're planning to use. If an outlier is an error and the correct value is known, correct it. If the unit is wrong, standardize it. If the observation is valid, we may simply keep it. Depending on the model, we may also consider transformations, robust scaling, or methods that are less sensitive to extreme values. The decision depends on why the observation is unusual and what problem we're trying to solve. So automatically deleting everything outside the box plot whiskers is a dangerous strategy. And this brings us to something that's easy to forget. Not every data quality decision can be made with Python. The data scientist can tell us that a value is unusual. The data engineer may tell us where the value came from, but sometimes only a domain expert can tell us whether that value actually makes sense in the real world. Good data comprehension is therefore not only a technical process, it's also a communication process. Exploratory data analysis, or EDA, helps us understand distributions, relationships between variables, unusual groups, and patterns that may influence our modeling decisions. EDA is not simply about generating as many charts as possible. Every chart should help us answer a question about our data. Now let's look at two numerical variables together. Here we're comparing lot size with sale price. The scatter plot allows us to see something that summary statistics cannot show clearly: how the two variables move together. If larger lot sizes generally correspond to higher sale prices, we may have a positive relationship. But visual inspection alone doesn't tell us how strong that relationship is. That's where correlation becomes useful. Pearson correlation measures the strength and direction of a linear relationship between two numerical variables. Its value ranges from -1 to +1. A positive value means that the variables tend to increase together. A negative value means that as one increases, the other tends to decrease. And a value close to 0 means there is little linear relationship. That word, linear, is important. A correlation close to 0 does not necessarily mean that no relationship exists. The relationship could simply be nonlinear. Here's a simple example. These two variables clearly have a relationship, but because the relationship is curved rather than linear, Pearson correlation can be close to 0. So never use the correlation coefficient without looking at the actual data. A scatter plot and a correlation coefficient should usually be interpreted together. If you watched my A/B testing video, we've already talked about PE values. The idea here is exactly the same, but the null hypothesis is different. In the standard Pearson correlation test, our null hypothesis is that the population correlation is 0. In other words, there is no linear correlation in the population. Now, Pearson gives us two pieces of information that answer two different questions. The correlation coefficient, R, tells us the direction and strength of the linear association observed in our sample. The p-value helps us decide whether we have enough statistical evidence to reject the hypothesis that the population correlation is 0. Using a significance level of 0.05, if the p-value is below 0.05, the result is statistically significant, and we reject the null hypothesis. If the PF value is 0.05 or greater, the result is not statistically significant, and we fail to reject the null hypothesis. Suppose we observe a correlation of 0.8 in a large sample. The observed relationship is strong, and with a sufficiently large sample, the PA value will typically be very small. So we reject the null hypothesis, and have strong evidence that the population correlation is not 0. But now imagine observing the same correlation of 0.8 in a very small sample. The observed relationship is still strong, but with so little data, the p-value may be above 0.05. In that case, we fail to reject the null hypothesis. That does not mean we've proved that there is no relationship. It means we don't have sufficient statistical evidence to conclude that the population correlation is different from 0. Pearson isn't always the appropriate correlation measure. In our dataset, we have variables such as VH-home quality and VH-home rating. Both are ordered variables. For example, a rating of 5 is higher than 4, and 4 is higher than 3, so the order clearly matters. But we shouldn't automatically assume that the difference between rating 1 and 2 represents exactly the same amount of change as the difference between rating 4 and 5. That's why Spearman rank correlation can be more appropriate here. Instead of focusing on the exact numerical distance between the values, Spearman converts the observations into ranks and checks whether the two variables tend to move in the same direction. So if houses with higher VH-home quality generally also receive higher VH-home rating, Spearman will capture that relationship even if the relationship isn't perfectly linear. Now let's look at the actual result. We get a Spearman correlation of about -0.18. The negative sign tells us that the two variables tend to move in opposite directions. As the rank of one increases, the rank of the other tends to decrease. But the magnitude is only about 0.18, so this is a very weak relationship. Now look at the p-value. It's approximately 8.39 times 10 to the power of -12, which is far below 0.05. So the relationship is statistically significant, and we reject the null hypothesis of 0 Spearman correlation in the population. And this is a perfect example of something we discussed earlier. Statistical significance does not mean a strong relationship. We have strong statistical evidence that the association is not 0, but the association itself is still very weak.
So far, we've looked at relationships between numerical and ordinal variables. But what if both variables are categorical?
In our data set, let's look at VH-home good schools and VH-home interest in home. We can start by creating a contingency table, which simply shows how frequently the different categories of these two variables occur together. Then we can use a chi-square test of independence to ask whether there is evidence of an association between them. Here, our null hypothesis is that the two variables are independent. In other words, there is no statistical association between them in the population. The PE value is approximately 0.45, which is greater than 0.05. Therefore, the result is not statistically significant, and we fail to reject the null hypothesis. We don't have sufficient evidence to conclude that these two categorical variables are associated. When we have many numerical features, a correlation heat map gives us a quick overview of their relationships. We're interested not only in features that correlate with the target, but also in features that are highly correlated with each other. For example, here we can see a strong positive correlation between VH-home pool quality and VH-home pool SQF feet. This tells us that larger pools tend to have higher pool quality values in this dataset. But high correlation doesn't automatically mean that we should remove one of these features. Pool size and pool quality represent different concepts, and both may contain useful predictive information. We can also see a negative correlation between VAC home cons year, which appears to represent the home's construction year, and VAC home quality. Rather than immediately removing one of them, we should first ask why this relationship exists, and make sure we understand how these variables are defined and coded. So the important point is, a correlation heat map is a diagnostic tool. It helps us find relationships worth investigating. It doesn't make feature selection decisions for us. A pair plot gives us a quick visual overview of both individual variables and the relationships between them. The diagonal shows the distribution of each variable. For example, sale price and lot size are clearly right skewed. The other plots show pairwise relationships. We can see a clear positive relationship between sale price and home rating, while sale price and lot size have a noisier relationship with some extreme values. Quality and rating form these bands because they are ordinal variables with only a limited number of possible values. So a pair plot is a useful screening tool for quickly spotting distributions, relationships, and potential outliers before investigating specific variables in more detail. Now we come to one of the most important problems in the entire machine learning workflow: data leakage. The test set is supposed to represent data that our entire development process has never seen. Here's a simple example. If we fit a scalar using the complete dataset before splitting it, information about the test distribution has already been used during pre-processing. Instead, we split first. We learn pre-processing parameters from the training data, and then apply exactly the same transformation to the test data. The same principle applies to imputation, scaling, feature selection, and many other pre-processing decisions.
Thank you so much for watching this video all the way to the end. In this video, we covered some very important topics around data preprocessing, exploratory data analysis, or EDA, and data correlation. These are essential steps that can help us better understand our data and ultimately build better machine learning models. If you found this video helpful, please support the channel by liking the video, leaving a comment, and subscribing. And stay tuned for the next video. See you next time.
See the raw data, a chaotic web of light, guiding all the glowing nodes and making them align, sorting out the distributions, putting facts in place, understanding every pattern in the shape of empty space, finding all the hidden signals, pulling from the noise. It's a conversation with a silent reasoned voice, not just generating graphics for the spectacle. Every single chart we're building has a purpose logical, framing up a pointed question that the answer can define, turning simple information into knowledge by design, turning simple information into knowledge by design.